Hey everybody, thanks for checking out the channel. Don't forget to like and subscribe. Oil viscosity is one of those misunderstood topics that I will try to explain. Part of the confusion comes from quotes like this from A Main Hobbies, and one of my sharp viewers pointed out discrepancies in the labeling on bottles of oil. On this channel, we look at the science behind our grown-up toys. Viscosity is a fluid property. It's the fluid's inherent resistance to movement. Sometimes it's also called thickness or weight. Thicker fluids move more slowly and resist movement more firmly. It takes more force to displace a thicker or heavier or more viscous oil. There are two measurement systems for fluid viscosity, metric and SAE, or American. Weight is the American measurement scale introduced by SAE, the Society of Automotive Engineering, in the 30s. 20 weight, 30 weight, 40 weight, etc. It's actually the same scale that's used for motor oil. For example, you probably know 10W40. 10 weight is the viscosity in a low temperature range, and 40 is the viscosity at a higher temperature range. The other measurement system is simply an international metric system, and the units are centistokes, or cSt. That's little c, big S, little t. The c is simply centa, meaning 1/100th, just like a centimeter is 1/100th of a meter. The other part is stokes. Just like meters, liters, seconds, stoke is the metric unit of viscosity. So why centistokes? I guess dividing by 100 simply makes the number on paper easier to use. Someone along the way thought it was easier to say 550 centistokes rather than 5.5 stokes. It's the same thing. Also, it's customary to specify the temperature at which the cSt measurement was taken. 25C and 40C are the two standards. I do know that associated numbers are at 25C, which is 77 degrees Fahrenheit, basically room temperature. And I can only assume other brands are on the same scale, but that might be a bad assumption. There's also a different measurement of viscosity called centipoise, or poise, which is a dynamic viscosity, and it's totally different than stokes. Centipoise is not really used in suspension design, so just pretend you never heard of it. Here is important point number one. Both stokes and weight are linear scales of the same fluid property. They measure kinematic viscosity, which is resistance to movement. You can contrast this to some other scales that are not linear, like decibels. Decibels is actually a logarithmic scale, meaning if you turn up the volume by 10 decibels, the sound is actually 10 times louder. Adding 20 decibels is 100 times louder. This will be important in a few moments. Viscosity is a linear scale. Compare it to millimeters, for example. Take 10 millimeters. 20 millimeters is twice as long as 10 millimeters. 100 millimeters is 10 times the distance of 10 millimeters. This is the same for viscosity. 20 weight is twice as thick and twice as slow as 10 weight. 500 cSt is twice as fast, or half the viscosity, of 1000 cSt. This is a fact that I can demonstrate, though it's not necessarily obvious if you're looking at the labels on the bottles. Also, both cSt and weight intersect at 0, meaning 0 cSt is the same as 0 weight. You can contrast this to other scales like temperature, where Fahrenheit and Celsius do not cross at 0. If you're still with me, here's where it gets confusing. I compiled the weight and cSt numbers that are printed on all the labels for Associated, LOCI, and XTR. I included XTR because they have much finer increments, and I was curious to see if this made their conversions more accurate. It looks like LOCI and Associated are translating from weight to cSt based on which numbers are even increments versus more random numbers, and XTR is going the other way. One of my astute viewers pointed out that a 20-point jump on the weight scale isn't the same on the cSt scale. So if you look from 20 to 40, that's a 20-point jump. And on the cSt scale, that equals a 200 to 500 to 300-point jump. Well, if you look down here, a similar 20-point jump 60 to 80 equals only a 200-point jump on the cSt scale. That's a great observation. So why do the published numbers on the bottle for loci and team associated not appear to make sense? Well, they actually do make sense, and I'll explain why. Let's apply some math to get to the bottom of this. Let's start by looking at the published numbers from team associated. This is a plot of the SAE weight numbers versus the cSt scale. You would expect a perfectly straight line, but that's not what we get. So what I'm going to do is add something called a trend line, which is a mathematical interpolation or simplification of all the data points. This is very easy to do in Excel. This takes data that is perhaps a little messy and gives you a mathematical equation that represents that data. We know that 0 SAE equals 0 cSt, so we will check this box to force the equation to go through 0, 0. One thing we can look at is the slope of the line. This is the relationship between the two axes. Slope is also rise over run, meaning the rise on the y-axis divided by the run on the x-axis. For example, take 500, which is the rise, divided by 40, which is the run, and you get 12.5, which is right here in the equation, 12.5. That's the slope of the line. So using 12.5, or 12.556 to be exact, you can now convert any SAE to cSt or vice versa, and it will be more accurate than the data or the numbers published on the bottle. The other thing we should look at is the R-squared value, which is called the coefficient of determination, which is just a fancy way of saying the quality of the trend line. A value of 1 would be a perfect fit. Anything in the 0.99 range is considered an excellent fit. Now, my assertion was that viscosity is a linear scale, which means a straight line. So let's try a couple other types of mathematical trend lines and see if there is something more accurate. This is a polynomial fit. See how the R-squared value increases to 0.9996? That's better than the 0.997 we had with a linear fit. However, here is where we have to use some engineering judgment. Notice that the line starts to curve at the top. Let's expand that and see what's really going on. If we extrapolate that polynomial equation, we see that the line curves and starts to move down. And we know that SAE 140 does not equal cSt 300. The viscosity numbers will continue to climb and never go backwards like this. So we should rule out a polynomial trend line and stick with the linear one. Remember when we were talking about the decibel scale? This is what a logarithmic trend line would look like. And we can see that it's not a fit either. I wasn't expecting it to be a fit, just showing you another possible type of trend line. Notice how the R value has gotten even worse, 0.919. Now let's look at data from 3 different brands. They are kind of all over the place. We'll add trend lines and compare. First, let's look at the slope. 12.8, 12.6, 13.5. Those are fairly similar. Let's take a look at the quality of the trend line. They are all over 0.99, which means that these linear trend lines are all excellent approximations of the data. Now let's look at all the possible data points on one trend line. I included some additional data points from Huddy and Traxxas. We'll do a trend line for them all combined together. When we do a trend line for all the data points combined together, we get a slope of 12.9, which is right in the middle of the slopes that we calculated independently. The R-squared value is still quite high. So I think it's a very safe conclusion that SAE to cSt data conversion is on a linear scale, despite the published numbers that are on bottles not always being a perfectly straight line. Let's look at one more thing. Let's go back to this observation by one of my viewers, which is a great observation, by the way. This 20-point jump on the SAE scale from 20 to 40 is a 300-point delta on the cSt scale. A similar 20-point jump from 60 to 80 is only 200 on the cSt scale. The reason is that we're looking at subsets of the total data. I basically cherry-picked some of the data deliberately with the most contrast, which is something you would never do when there is more data available. Neither of these lines represent the overall slope. Make sense? You want to look at all the available data points before drawing your conclusions. And in this case, we should still conclude that the scale is linear. I want to look at just one more thing. It looks like the line doesn't quite go perfectly through the visual center of the data. It's a little high here, and it's a little low up here. It looks like when we set the 0, 0 point, the line tilted a little bit. Remember, 0, 0 is a data point that we essentially added based on our engineering judgment. 0 SAE should equal 0 cSt. That's a very reasonable assumption. Well, we have the tools to see if this is correct or not. So let's turn off the 0, 0. The line has now shifted visually. It looks like it lines up with the data a little bit better. But look at the R-squared value. It was 0.995, and now it's dropped to 0.985. So without the 0, 0 point, the trend line is actually less accurate. That is just one more point of evidence that supports our conclusion. The conversion between SAE and cSt is in fact linear, and the labeling on the bottles from the manufacturers has some irregularities. So why are the published numbers so goofy? There's definitely some convenient rounding taking place. It seems unlikely that both scales are always exact whole numbers. We don't know if the numbers were measured in cSt, then converted to weight, or measured in weight and converted to cSt. Or perhaps each scale was measured on different machines. We also don't know what temperature was used. Finally, there's always going to be error in measuring something. There is the manufacturing tolerance. 100 cSt is almost never going to be exactly 100 cSt. Realistically, it's probably 95 to 105, somewhere in there, best case. There are also errors in the gauge used to measure the oil and errors coming from the person operating the gauge. I'd be more suspicious if all the data was a perfectly straight line. So what does this mean for us trying to tune a vehicle? We've established that oil weights are linear within a manufacturing tolerance. We've also established that the labeling is not consistent. The numbers on the bottle are not always exact. I recommend that you consider the number on the bottle to be nominal, just a name. They might as well be labeled A, B, C, D, E, F, U. Consider the numbers to be relative to each other and not absolute numbers. Say your baseline is 50, well, 55 is a little slower. 60 is a little more slow. 100 is twice as slow. You're going to tune in a relative manner anyway. There are super complicated equations that predict oil behavior and oil flow, but it's way too burdensome. You're going to figure out your oil weight through testing. You can contrast oil weight tuning with spring rate selection. I can tell you almost exactly what spring rate and preload to use based on your vehicle's weight, the weight distribution, and your target ride height. But oil weight is so much more complicated, it's better to be based on feel. There isn't simple formulas. You're going to fine-tune your oil weight based on wherever you are today and where you want to go. So when it comes to picking shock oil, ask around, get a starting point, and make changes based on your driving style and preferences. Check out my video on oil weight and you'll understand my approach and why I run a very light 20 weight oil in my crawler. There's no right and wrong when it comes to oil weight. You do you. It's also smart to stick with one brand of oil. That will increase your chances of better consistency across the range. Shock oil is cheap and bleeding is relatively easy. Don't be afraid to experiment.